Hola y bienvenidos al videos de cálculo. Para continuar en inglés, oprima 1.
Did you actually press the 1 on your keyboard? I hope so, because that would be fun. Hey, hopefully you're in a really good mood right now because you're at home instead of at school. And hopefully you remember to bring home your packet so that we can talk about a little bit of calculus so we don't get behind. What I want to talk about in this video and the next video is something called parametric equations. It's a different way to represent the motion of something, which is why this is the third time that we're looking at motion in this class. And we learned about derivatives, we learned about how to get from position to velocity to acceleration, and we talked speed, and then when we learned about integrals, we went back and figured out, well, how do we get displacement and total distance traveled and things like that. This is our third go around now with motion, so if you're getting a little bit exasperated, do you know, by the way, you know you can write these two punctuation marks together, like you can do that, and it's but then it's got an exclamation point in the middle of it too. That looks too much like a P, but you can actually do that. It's got a name. It's called an interrobang. That's a real thing. You can look it up. Now, right now, because we're doing calculus, pay attention. So, why are we at motion a third time? Well, it's because pretty much all the motion that we talked about so far has been straight line motion. Just a particle moves along the x-axis, or a guy rides a unicycle, east and west, or a particle just moves up and down. But in the real world, very rarely will something just move in a linear fashion. It'll move all over the place. And so the problem with that in terms of what we do with single variable calculus is we can't really look at an x direction and a y direction as two variables in the same equation, because then we try to do calculus with more than one variable, things fall apart on us. So what parametric equations do is sort of get motion in both the x and the y direction defined as a single variable. And that variable, if you think about what we've done in the past to sort of get around motion of things in more than one direction, that variable is time. So we have here is a particle moving along the Cartesian coordinate plane is the fancy name for the x and y axis. They just happen to use Cartesian in the book. If you know who Descartes is, he's the guy who names Cartesian there. If you don't know who Descartes is, I don't care. So as a particle moves along the plane according to the parameters. Parameters are equations that guide the motion of your particle. And you'll notice here there's a parameter for the x variable, for the x direction, and a parameter for the y variable. And both of those parameters are in terms of time. So as time passes, the particle is at different x coordinates and different y coordinates. I was going to bring a tennis ball and bounce it all over the place so you could think about motion happening in both directions. So if you're given these two parameters, and this is t squared minus 2t for your x parameter and t plus 1 for your y parameter. First, I just want to talk about how we find the location of the particle when t equals 1, for example. Not surprisingly, you just substitute 1 in for t in both places. So the x value is going to be 1 squared minus 2 times 1, so that'd be negative 1. The y coordinate is going to just be 1 plus 1 is 2. So when t equals 1 second or minute or whatever the time span is, after the beginning of the motion, the particle will be at the point -1, 2 on our coordinate plane. And we'll look at that on the next slide about what that looks like on our graph. But if you are looking just for the location of the particle at any point in time, it's a simple substitution and find a value for it. So when t equals 2 squared minus 2 times 2, 2 plus 1 for the y coordinate. T equals 3, so 9 minus 6 would be 3. 3 plus 1 would be 4. So for different points in time, you have different positions. I shouldn't say position because I don't want you to be thinking displacement and that. So different locations on your coordinate plane. And I went ahead to speed things up since I know you want to go out and go sledding. I just did a bunch of different t values. We're going to actually include some negative t values in this problem, just so we can get an overall sense of what the graph looks like. And so here's fast forward to a whole bunch of plugging in t values. We've got for different values of time between -2 and +4, we've got different x coordinates and different y coordinates, and I've gone ahead and graphed those on your coordinate plane for you. And when t equals -2, we're plotting the x and the y here. This is still our good old x and y axis here. There's not a t-axis or anything, it's just at different points in time. We're at different points on our coordinate plane. And here are all those values that I found just by substituting t values in and getting x's and y's out. So you see all the points that are plotted here. In a parametric curve, since the time is passing from obviously smaller values of time to larger values of time, you will see this graphed as a regular graph here. So like starting at -2 and coming along here. I probably should have done this off camera so it won't look terrible, but it's going to look terrible like that. So it looks kind of like a parabola flipped on its side, and we'll see that that is the case here in a second. But in addition to having the shape of that graph, you've also got a direction to that graph. And there's usually little arrows indicated along the way that, you know, hey, I'm going this way. I'm starting from the smaller t values, or maybe in a different problem, you might just start at t equals 0 and say, look, I'm going in this direction. The particle is moving in this direction over time. So if you ever see one of these graphs and you see those little arrows, that's what they're talking about there. So that's how you take parametric equations and plot points on our regular old xy plane. So it looks like a parabola here. There is a way to write the equation of this graph just in terms of x's and y's, obviously, since it is on our regular x and y axis. And so I wanted to show you that here. Let's figure out how could we get the equation of that graph ignoring the parameters, ignoring that time. How can we just get it as a relationship between x and y? So I've written the parametric equations here again. And the way to eliminate those parameters is to make a substitution for t. Take one of your parametric equations, solve it for t, and then substitute that new expression in for t into the other parameter. Here, it'd be much easier to solve this one for t, so I'm going to do that first here. I've got t equals y minus 1, and I'll take that expression for t and I'll substitute it in to the other parameter. So now instead of x being in terms of time, x is going to be in terms of y minus 1 squared, minus 2 times y minus 1. And then I'll go ahead and finish this. I'll do some algebra and get this to look like a quadratic equation. That's a plus 2 there. So this ends up with x equals y squared minus 4y plus 3. That would be the equation of that parabola on its side, just in terms of x and y. Note, it looks like a quadratic equation, but the y is the quadratic variable. It's the y that's getting squared. That's why the parabola is on its side. That's why that wasn't a function. You get, vertical line tests, things like that. But I don't think that you'll be asked to do something like this. Pretty much everything that you'll see on the calculus exam, on the BC exam, will deal with how to handle the calculus of the motion of the particle or whatever, and so we'll talk about that in the next video. But I wanted you to have a foundation of what these parameters are about and how we could maybe write something in terms of just x and y again. I've got just one more thing here that I want to get some trig involved because there are some problems in the assignment that you're going to be doing trig. I also ran out of, I've only got 4 of these boards now. I took the rest of them back from me, so I'm just going to have to use our actual whiteboard for this one. If we have parameters in terms of trig here, usually they'll give you an interval so you don't just keep going around the unit circle forever with values of time. Do this the same way we did the other one. Just start plugging in values for t and getting x's and y's out of there. You're going to be able to use your calculator on all these problems, so this doesn't turn into you trying to remember the unit circle or anything like that. You would just start choosing t values that are useful, you know, that are easy for you. Just maybe make a little table here where go to 0 and pi over 6 and just your normal family of functions there. Hopefully you can see the bottom values there. And then get your x by doing 3 times cosine of t, and your y by doing sine of t. So get all your points, and then you can plot them along the way. So that'd be I guess 3 radical 3 over 2, and so on. Again, you can use your calculator to speed these up. I just want you to be able to get a feel for what the motion looks like, what the location of the particle or whatever is on the coordinate plane as you go. All right, so just write these in here real quick, and you'll have some x's and y's that you could plot along the way. And I think what you'll find if you plot those is it's going to look like an oval shape or an ellipse. I think we talked about equations of ellipses for like 1 minute when we were in pre-cal. So obviously you remember everything about it. Don't worry about that so much. Actually, the book asks to kind of connect those things, but all I think I would notice is you do know one trig identity that would really be helpful here to connect these two things. Like if that 3 weren't there, remember that cosine squared plus sine squared equals 1. All right, that's the one trig identity we try to remember. So if you rewrote this one, if you just said, hey, you know what, this is I could write cosine of t as x over 3, and I've already got y equals sine of t. Since you know that cosine squared plus sine squared equals 1, you could just do this thing squared. I might be one too high up on the board here. You go this thing squared, so I'll turn this into x over 3 squared plus this thing squared plus y squared equals 1. That would be a way to eliminate that parameter and get your equation just in terms of x's and y's again at the end. So I think that's a trick you can use, and I think it's 19 through 21 you're going to do at the end here to kind of eliminate that parameter, or just plot some points and follow the motion along your coordinate system. So that's an idea of how parametric equations work. Go do those few problems. There's not very many of them. Get your calculator out to speed things up, but make sure you come back tomorrow with a good understanding of how parametric equations work. And then if it snows again, the next video we'll talk about the calculus of how we deal with parametric equations.